Okay. Okay. So thanks, David. Yeah, so what I'm going to do in the next about 45 minutes is going to really tell you a little bit about neural nets. The official title given to me is Introduction to Neural Net. Uh, it doesn't work, or I have to use this. Okay, yeah. Okay, so yeah, the official title given to me is Introduction to Neural Nets, but I've also been told that, lots of people probably don't have a lot of math background, and I've been asked not to tell you a lot about the math behind all the neural nets, and I promise that I won't do that. So the unofficial title is the ABC of neural nets without much X, Y, Z. Okay, so I still need some X, Y, Z there. Otherwise, you really won't be able to see what's going on behind neural nets. But I promise that there will be just high school level mathematics. So before, I promise. Yeah. So before I move on, let me check. Is everyone comfortable with the vectors, matrices? Yes. Yeah, yeah, at least you know that these things, right? Okay, so that's good enough. That's all we need to understand what's going on. Probably one more thing is about derivative, but we'll talk about later. Um, yeah. So why are we interested in neural nets? Neural nets are part of a machine learning. In the past, neural nets has not been that popular. They actually just become really popular in about last 1 decade. So before that, the godfather of deep learning, Geoffrey Hinton, said that around even 2000 he found it very difficult to publish papers, neural net papers. So if you have like a neural net in your paper title, then people think that, oh no, you must be doing crappy work. You are not doing serious machine learning. So that's basically what happened like about 20 years ago. But over the last one a decade, well, 2 decades, things have changed a lot. Now we find neural nets everywhere. You certainly have been using all kinds of virtual assistants using in your phone and computers, etc. And I'm sure that everyone use all these chatbots and coding agents nowadays. So even if you never written any program before, you can ask the chatbot or the coding agent to help you to solve actually pretty difficult problems. Of course, the difficulty part is how do you know that whether the agent is giving you some correct answers? Yeah, so that requires a lot of training. I think that goes back to what Lee mentioned earlier. Although AI is really very helpful to help us speed up the process, but you still need that kind of expertise to understand whether AI is generating some meaningful solutions. That's something that can be replaced. There are other examples that I'm not going to talk about here. One thing that I want to mention is that AI has been used a lot in science. For example, weather forecasting and battery design optimization, and certainly in agriculture as well. There are many examples that you are going to hear in the next few days. Some of the speakers will tell you about how neural nets are actually used in their work. So that's the part I'm not going to talk about. Okay. Oops. So what am I going to talk about in this talk? Uh, okay, so everyone like a crystal ball. So of course, Lee has a much nicer crystal ball than mine. Yeah, yeah. And there are some myths going on behind all this neural net stuff. Actually, lots of myths. Sometimes people say that now neural nets have consciousness. For me, I always feel that that's a little bit, not quite true. They are still programs, numbers. Maybe indeed our human brain shares some similarities, but I really don't feel that now AI is conscious. Lots of buzzwords going on there. And and in a lot of cases, when people use neural nets, they treat them as black boxes. So you hope that now if you simply ask AI to write some neural net code, AI will give you the neural net code. And it's like kind of like the crystal ball. They will give you the answer and you stop there. And sometimes they may mess around with the training process a little bit and tune the so-called hyperparameters of neural net. But again, probably not much understanding is going on behind that. That's not what we want to do. So in this talk, hopefully that at the end of the talk, you understand what neural nets are and understand a bit about the training, how you train the neural nets to make them work. Okay, so that's what we'll talk about in this talk. So there are a few 101s here. Anyone with a machine learning background here? Yeah, actually that's pretty good. So hopefully this will not be too boring. Machine learning is such a big field. If you really want to understand all the algorithms in machine learning nowadays, it's impossible. But behind nearly all the machine learning algorithms, though not all the machine learning algorithms, you can describe these algorithms as solving some kind of optimization problem there. So you have some kind of models that you want to fit. So that may be as simple as linear models that you use in linear regression. And then you have some data. Then what you want to do is you want to calibrate the parameters of the model so that the model fits the data well. That's basically what machine learning is in a very loose sense. There are more sophisticated machine learning algorithms that can be described always by this kind of optimization problems. So if you have already seen linear regression, you should consider that you have already seen at least one machine learning algorithm here. So if you haven't seen, let me briefly explain what that means. For linear regression, what you mean is essentially you are trying to fit in low dimensional space, you are trying to fit a straight line that interpolates the point. In high dimensional space, you are trying to find a hyperplane, just a plane to fit the points. So that's the kind of function that we are working with, a linear function of the features or variables or covariates, whatever you call that you observe. And then you have some values that you want to predict, some numbers that you want to predict. Okay, and then you just fit this kind of linear model by minimizing the mean square error. So that's the general structure of machine learning. So what is a neural net or deep learning about? It's basically now replacing the functions that you are considering or models that you are considering by the so-called neural nets, which are rather complicated mathematical functions that you don't want to write down, but conceptually they're very straightforward. We are going to see what exactly neural nets are and how you can optimize, solve this kind of optimization problems in the next few slides. So that's the neural nets 101. Neural nets are basically mathematical functions inspired by biological brain. The idea is if you connect lots of simple computational units together in some meaningful way, then you will be able to do really complicated calculations, just like how our brains do. Our brain have lots of very simple neurons. They do very simple things, but if you connect them in some way, and then they can do really complicated things. This is not to say that indeed the artificial neural nets that we are talking about reflect how biological brains are working. In early neural nets papers, indeed people often draw a connection to biological neural nets, but in fact there isn't much connection between how artificial neural nets work and biological neural nets. The architectures are still very different. So that's what a neural net is. You can define the so-called simple computational unit in whatever way you want, and you can also define the kind of networks in whatever way you want. That can be considered as a neural net. Lots of flexibility there. The interesting thing about why these neural nets can work so well is they are the so-called universal approximators. In the sense that if you want to learn some kind of complicated relationship, and then you consider a flexible enough class of neural nets, then it's guaranteed that within that class, you can find a neural net that approximates the complex functional relationship very well. Yeah, very loosely speaking, that's what that means. Basically, they're very expressive mathematical functions that can approximate any kind of functional relationship that you want to learn. In standard neural nets, what you typically do when you define the so-called neuron is here. This is where the math comes from. You need to do some simple vector operations. So what you do is if you have some input or the variables, input variables, you combine them in a linear way. So you simply multiply the so-called weights with these inputs, and now you get the weighted input sum, or the dot. You can write it down as the dot product. After that, they apply some kind of transformation to this dot product. For the kind of transformation that people typically use, they are quite simple. So we are going to see a few examples there. So they can be something like the so-called sigmoid function, which squash the real axis into just a small interval, between 0 and 1. No? So there are other examples there. Yeah. So basically, that's a one slide description of what a neural net is. Okay. So if you have any questions, just feel free to raise your hand. Quick questions. Okay. So I'm going to tell you more about this neural net. Even though conceptually you can describe what neural net is in just a single slide, but that's not enough for you to apply neural net well to solve the problem. There are some typical architectures that people have found out to work well on certain kinds of data. And I'm going to talk about the so-called multi-layer perceptrons, convolution neural nets and recurrent neural nets, a few neural net architectures for dealing with the different kinds of data. And I'm going to say a few more words about how we can actually solve the optimization problem. Now you know how you can define the model, but how do you actually fit those models? For these models, they are typically fit using the so-called stochastic gradient descent algorithms and the variants of this algorithm. In this talk, I'm just going to focus on this algorithm, although there are many others that are used in practice. In fact, the ADAM algorithm is probably one of the most commonly used algorithms. I think the paper has probably more than 60,000 citations now. Yeah, huge number of citations. And I'm going to tell you a little bit about how you can actually get your hands on using the PyTorch library. Okay, so about the optimization. Has anyone learned gradient descent before? Yes, okay, that's great. Yeah. The idea behind gradient descent is very simple. So imagine that now you are trying to go downhill. And kind of you have superpower, you can go along any direction. You're not afraid of falling down on the hill. And which direction are you going to pick so that you can actually go down the hill as fast as possible? And then what you're going to do is, you're going to actually now just scale the directions and then take the steepest direction, right? Yeah, if you really have the superpower, so you're going to follow the steepest descent direction. That's basically what gradient descent is doing. You pick the steepest descent direction and then move along that direction. You can write this down pretty nicely using just a single formula. So if your current location is represented, or your current solution is represented by this vector W, and what you are going to do now is you want to minimize the function LW. So you simply calculate the gradient, and then you move along the negative gradient direction. So the method that we use here is the steepest descent direction is the negative gradient direction. Okay, yeah. So that's a gradient descent. Let's look at this concrete function as a concrete example. So if you plot this function, this is a function with the two variables, and this is how the function value or surface looks like. If you plot the gradient, this is how the gradients looks like. It's a little bit smallish, but you can see all the arrows represent the gradient, magnitude, and the direction. All the arrows, they are pointing away from the minimum, which is 0 and 0. Right? So, but if you reverse the direction, then they are kind of pointing towards the minimum. So this is showing that indeed, if you move along the negative gradient direction, it's likely that you are going to move a bit closer to the minimizer. Yeah. And let me show you a visualization. Oops. Uh, yeah, thanks. Okay, so this is a visualization that I developed with a few other colleagues. Now let's pick a, well, let's just pick this function. I don't know why that. Okay, so I just pick this function. Let's see. So we are starting from the point 0.5 and 0.5 here. And what the color means is hotter means a larger value and cooler color means smaller value. The minimum is here. What happens if you do gradient descent? Now let's step through a few iterations. So you can see that when it moves along the negative gradient direction, indeed, it moves a bit closer to the minimizer. So you can keep on doing this, and eventually then you are going to move to be as close to the minimizer as possible. You are never going to hit the minimizer in this case, but you will get close enough for the solution to become useful. So that's how gradient design works. If you want to have some more fun by playing with the other kinds of functions, you can do this. So you can choose different kinds of objective functions, like the univariate functions and some other bivariate functions like this one, which is very complicated. And there are many other optimization algorithms that you can play with in this case as well. So I only cover gradient descent in this talk, but there are more effective algorithms for solving this kind of optimization algorithms. So I'll leave it to you to have some fun after the talk. Okay. Oops. Sorry. Oh shit. Okay, yeah. And when you train neural net, um, you don't use a gradient descent directly. That's the part where things become really very interesting. You use the so-called stochastic gradient descent. That's a stochastic version of a gradient descent. Where does stochasticity or randomness come from? What you do is instead of trying to minimize the loss function defined on the data set, on the entire data set, you simply pick a random subset of the examples and calculate how well the model fits on that data set. And after that, then you take a computer gradient for that approximation, move along the negative gradient direction. Yeah, so that's the stochastic gradient descent. Essentially, at each step, you deal with just a random subset of the original data set and apply gradient descent. If you apply gradient descent to minimize a function similar to the one that we have seen before, you are going to get a smooth trajectory that looks like this. But if you apply stochastic gradient descent, you are going to get a pretty zigzagging that trajectory like this. By looking at this example, you may feel that now, why should this kind of randomness be helpful? Yes, for toy problems like this, stochastic gradient descent doesn't work very well. But for neural net training, when you're dealing with the large data set, stochastic gradient descent somehow just works like a magic. We don't fully understand why they work so well. So that involves very complicated mathematics. So people have been, developing mathematical tools to understand why stochastic gradient works so well, but we don't have a complete understanding on that. At a high level, what we know is by using stochastic gradient descent, you save a lot of computational resources. That's because for very large data sets, even if we want to calculate the gradient on the data set once only, it takes a huge amount of time. It's not practical at all. But with the stochastic gradient descent, it's possible to do that. So you can do that very efficiently. And at high level, we also believe that the reason that this stochastic gradient descent works so well is because when you are dealing with a large data set, actually there are a lot of redundancies there. So even if you are just sampling a small subset of the data set, when you calculate your fitness metric or loss, that gives you a reasonably good approximation. Yeah. And one last thing is, if you really try to visualize the loss function in an extremely high dimensional space, it will be an extremely ugly function with a lot of local minimas that can trap you. Now, if you use a gradient descent, there is no way for you to escape local minimizers. But with a stochastic gradient descent, it's possible for you to jump out those local minimizers. So we do have some high-level understanding of why stochastic gradient descent can be effective for neural nets. Okay. So to apply this gradient-based learning algorithm, you need to be able to calculate the gradient. It's actually not an easy thing for humans. Even in your calculus courses, when you try to work out the analytical expression for some math functions, it can be very tedious thing. The good news is for neural net, you don't have to actually do this gradient calculation yourself. You can use a technical or automatic differentiation. Here is an example. This is the code written in a library called PyTorch. Let's say that you are looking at the square of the magnitude of a vector x. So this is what it is. You can define the function as this. So if you want to calculate the gradient in PyTorch, you can now at the point 1 and 1. Yeah. So what you need to do is you evaluate the function at this point. After that, then you simply call this a metric function called backward. After that, then you will be able to retrieve the gradient of the function with respect to x. Yeah. And you can replace f by anything that's differentiable. So of course, you can replace that by neural nets, a much more complicated function. So that's how you can actually get the gradient without much effort. So that's about the optimization basics. Now we are going to move on to a few commonly used neural net architectures. The first class of models that I'll talk about are so-called multi-layer perceptrons. So this is the class that I'll be focusing on quite a bit. For multi-layer perceptrons, the neurons are organized into layers. You can see here, we start with the input layer, which consists of just the input, and then you introduce some neurons here in this layer, another layer. Eventually, you have some so-called output neurons. These are the numbers that you are actually interested in. And these hidden neurons, they define some intermediate computations. If you write these neural nets down mathematically, what you need is you need just some matrix vector calculation. So you can actually represent, for example, neural nets like this using a formula that looks like this, a pretty compact formula. I'm not going to explain the specifics here, but just remember that if you really want to understand what's going on behind multi-layer perceptrons, you can actually represent that using simple matrix vector calculations. Yeah, to make things more concrete, this is a toy problem where you have just two input neurons and two hidden neurons plus one output neuron. So it takes in two real numbers and outputs one real number. We need to specify the so-called activation functions for the hidden units. In this case, we use the sigmoid hidden units. Now let's start through the calculation a little bit. If you can calculate the output for each neuron separately. If you start with this hidden neuron, what you do is you calculate the weighted combination of the two inputs. And the weights are indicated by these numbers here. So it's 1 times x1, and then 2 times x2, and that will give you the output, the weighted sum. And then you need to apply this activation function, which is a sigmoid function here, to the weighted sum. So I don't have a paper here, but basically the answer that you will get is you will get this number as the output for the first hidden neuron. Okay. And then similarly, what you do is for the second neuron, you compute the weighted sum for these two inputs. So you get 0 times x1 and then minus 1 times x2. So you get minus x2 here. And then you apply the sigmoid function, then you get this thing. Then you apply, calculate the weighted combination of the outputs of these two hidden neurons. Then you get the final output, which looks like this. Okay, so if you trace through the calculation, you will find out that this is the final expression, and you can also write it down using matrix vector calculations. So that's one example, the toy problem. Earlier, I mentioned that neural nets, many neural nets, they are universal approximators. For multi-layer perceptrons, even if you consider the class of multi-layer perceptrons with just a single hidden layer, they are universal approximators. For example, you can actually use just a single hidden layer neural net with the two hidden units to approximate the quadratic function, and you can also use it to approximate the sine function. The final formula that you will obtain will look something like this. Okay, so the details are not important here, but just to convince you that indeed you can write down functions, arbitrary functions using neural net approximators. Okay. So these are very expressive functions. And how do we use these functions for solving problems that we are interested in? For example, let's say that we want to solve a regression problem. For solving regression problems, you define a multi-layer perceptron with just one output. And the loss function that you often use is the mean square error. Yeah. And after that, then you can run stochastic gradient descent to solve the problem. Let me give you an example here. We are interested in predicting the AOI from the reflectance spectrum. Assume that now we only look at 5 bands and calculate the value for the kind of weighted average value for these 5 bands. So we can get data sets that's similar to something like this. 5 input values. We want to predict the leaf area index, which is just a roughly measure of how large your leaf is. You can load the data set. After you load the data set, you can split the data set into training set and test set. Why do we want to split this into 2 parts? That's because in machine learning, we care about generalization performance of the data. So you train the data on one part of the data, but you want to see whether the model learned from the training data generalizes as well on a separate test set. And this is how you can do it using the so-called scikit-learn library, which is just a few lines. So you can build a linear regression model using 2 lines. If you want, you can make it just a 1 line. And then you can calculate the R-square matrix using the dot score function. Yeah, so very simple. That's how you can do a traditional linear regression model. Now you can similarly do that for building a multiple MLP model. What you need to do is you need to specify the network architecture and specify some of the training parameters. I'm not showing everything here. I'm just showing that here you are dealing with the MLP with a single hidden layer that has 50 hidden neurons. And when you do training, each time you use when you use stochastic gradient descent, you sample 32 random examples. Yeah. And the number of iterations they use is 10,000 here. Yeah. So you can see the syntax is pretty simple. You can actually get your hands on building this kind of a model really very quickly. Just in a few seconds time, then you can get this done by copy and paste the code. So PyTorch is a much better library for doing this. You need to specify the architecture of the neural net yourself. You need to say what are the layers. So in this case, you start with the 5 input variables that corresponds to the 5 bands, and then you say you have 50 hidden neurons, and then you apply the so-called ReLU activation, and then finally, then you have a one output. After that, then you say you want to use the stochastic gradient descent optimizer. You have the mean square error as the loss. This is the so-called data loader, which helps you to create small random subset from the data set. Okay. And this is the stochastic gradient descent iteration. You do that for 10,000 iterations. And now at each iteration, what you do is you actually look through the data set. So here, X and Y, they have 50 examples only. Okay, so then you calculate the loss, and then with the loss dot backward, that allows you to calculate the gradient, and with this opt step that takes one gradient descent step. So a lot of the details are taken care of for you. When you build your model, essentially what you need to do is that you can this is the parts that you need to work on, define the model architecture, and then you need to specify some of the parameters here, like the model, how many neurons that you want. And then for all these optimizers, you can specify some parameters as well. These are the details that I'm not going to go through. But at high level, it's about define the model, and now configure your optimizer. Then you do the stochastic gradient descent. Okay. Similarly, you can use MLPs for solving classification problems. If you have a K classes, let's say that now you are looking at some handwritten digits, and you want to recognize the numbers, let's say 0 to 9 in the digits, then you have 10 classes. And then what you will do is you have 10 output neurons, with each neuron indicating the score for each class. Okay, how do we train this model? So this involves a bit more mathematics here. What you do is you take the output. In this case, let's say that you output k numbers here. Then you first apply the so-called softmax function to turn these numbers into a probability distribution. So they sum up to 1. And to do this, what you do is you first exponentiate all these numbers. Then you divide all these numbers by the sum of them. Yeah, that's what the softmax function is. And then now you get a probability distribution. After that, then you maximize the likelihood or minimize the log loss. So that's how you typically train a classification network. Now, let's look at how we can do this for a simple example. For the iris flower, there are different species. If you measure the petal width and length and the sepal width and length, then you get 4 different numbers. By looking at these 4 different numbers, you can differentiate different species. So the data sets that you deal with looks like these 4 input numbers, and you have the species for the different iris species as the label. This is a standard data set that you can try out. You can simply copy and paste the code and run and the code with a few additional lines for importing the libraries. Yeah. Logistic regression is a very classical model that can be viewed as a special case of multi-layer perceptron with just single alpha neuron. This is how you can do it. Just using 2 lines of code by declaring the model and then fitting the model. Everything will be taken care of for you in this case. And you can also train an MLP classifier using sklearn. Of course, if you want to make the model well, typically you need to specify some of the hyperparameters and try different combinations. Yeah, this is how you can do it in PyTorch. The structure of the code is pretty much the same. Yeah. You declare the model, And now this is configuring the optimization algorithm. The main difference is in the loss function. Instead of using the mean square error, which is for the regression, now you need to use the so-called cross entropy loss, entropy loss. Essentially, that's what the formula here. Okay, yeah. Yeah, then the other things are pretty much the same. Okay, yeah. Okay. I hope I'm not frying too many people's brain now. Yeah, very good question. So the question is really, do you have to get your brain and fried in order to understand all this? I would say that you certainly don't have to understand all this before you can start coding. Even if you just ask ChatGPT, you can get some kind of initial code, and in a lot of cases they actually run pretty well. The point is, if you want to build really good models, and if something goes wrong, you need to be able to ask the right question. This is when you have to fry your brain a little bit. Yeah. Okay.
Can I just quickly ask a question for
Yeah.
something that might help clarify some things, Nan? When you showed the multi-layer perceptron, right, and inputs come into the input neurons,
Yeah.
and they get multiplied by the weights,
Yeah.
and then that gets aggregated at the next layer of neurons and so on.
Yeah.
How do those weights get established in the first place? Where do those weights come from?
Okay. So now let's go back to this example. The question is, where do all these weights come from? Right. You need to learn these weights. So initially, when you do this, you initialize them during training. You initialize these values to some random values. After that, then you apply stochastic gradient descent. So that's pretty much what we are doing, like in this picture. Imagine that this is the loss, the objective function that you are trying to optimize. This is the surface. What you do is you pick a random point in the parameter space, and then you start running gradient descent to minimize the loss, and eventually try to move towards the minimizer. Does that answer your question?
So would you say then that the data goes in, travels along through the network,
Yeah,
makes a prediction,
yeah,
assesses how good or bad that prediction is relative to what's the known answer, the truth,
yeah,
and then adjust the weights accordingly, right?
yeah,
And
exactly.
you do that over and over. Is that the training process? Yes.
Yeah, exactly. Exactly. So it all goes back to this equation. So what you do is if you have this is a neural net with some parameters. So what you do is now you feed the data to the neural net, then you can measure whether the neural net agrees with the target output. And then you can have some kind of agreement measure like MSE in the case of regression. And after that, then you run algorithms like a stochastic gradient descent to optimize the weight. Okay, I hope that this makes sense. Yeah. Yeah. Okay, now let's move on to. So basically, I've already covered the kind of the most important messages that I want to say. I just want to briefly mention two more architectures that people often use. These are convolutional neural nets and recurrent neural nets. For convolutional neural nets, these are particularly good for dealing with the image data or array data. They are similar to the multi-layer perceptron where you organize the neurons into a few layers, but they have a bit more sophisticated architecture. I think I'll probably will just skip these details for the interest of time. There are many applications. For example, you can use convolutional neural nets to classify images. If you take a photo of a crop and you want to know whether it has disease or not, that's one possible application. So, or you want to know whether it has a specific disease, that's also a classification problem. You can also do that. There are some more surprising applications. You can actually use convolutional neural nets for speech and natural language tags. So you can actually represent speech and natural language as some kind of tabular also array data. So that's something I'm not going to go into the detail. Yeah, let me skip how this actually works and only briefly mention the recurrent neural net. So recurrent neural nets are particularly good for dealing with the sequence data like a time series or text or speech data. And essentially, this is how recurrent neural net looks like. They are also inspired by how our brain process, sequence data. Each time step, if you have already seen something, then you can compute some kind of summary for what you have seen, and then you can fit this summary to the next time step. But each time step, you can essentially reuse the same kind of a neural net for doing this kind of processing. Yeah. So this is where the term recurrent comes from, because each time step you are actually using the same kind of a neural net for doing the computation. Yeah. Okay. I'm going to use two formulas to fry your brain a little bit more. So this is how you can summarize the computation in a recurrent neural net. The H is the summary of the past information that you have seen, and this is the input at the current time step. Then based on the summary of the past information and the input at the current time step, you can compute a new summary for the information that you've seen so far. And based on this, then you can make some predictions. Okay, so that's how a recurrent neural net looks like. I'll wrap up by just saying that neural nets, they can be very complicated, and it may feel like a complete black box. But in some cases, if you look at the neurons, those hidden neurons, you can actually interpret them in some way. For example, if you use a convolutional neural net to recognize faces, you'll see that some of the neurons, hidden neurons, they are able to detect whether there is a nose there are eyes there, etc. So they are learning some high-level features based on just a low-level pixel values. So that's something that I think the next speaker will talk about, about how neural nets can generate very high-level features. If you train neural nets on lots of data, you can reuse the learned features and for all kinds of downstream tasks. So I'm going to wrap up my talk. So this is what covered in this talk. I think the key takeaway is machine learning is basically about specifying a model and then solve the optimization problem of fitting the data. That's true for a lot of cases. And what's neural nets about? Neural nets are basically just highly expressive mathematical functions motivated by human brain. They are typically fitted using the so-called stochastic gradient descent algorithm. These are some of the commonly used architectures that I mentioned. Yoni will talk about the transformers. This is a kind of the most important architecture in natural language processing, but recently have also become so important in computer vision. Going beyond this talk, people will talk about how you can, you learn high-level features using neural nets. That's what we will talk about, and I think David will talk about foundation models. And if you combine neural nets with the task-specific tools, then you can have agents like the coding agents. Okay, yeah. So that's all.
Thank you, Nan. We have time for a question or two, just quickly before we head out for morning tea. So I think I just saw a hand up. Yep. Down there. Okay.
Hello. Hi, Nan. That was a really beautiful ABC intro. I've got a really dumb question. When you're sampling the space for the stochastic gradient descent,
Yeah.
sometimes it's 32, sometimes it's 50. Is that number?
Sorry?
The batch number, the number of times you're sampling,
Yeah.
is there a rule of thumb for that when you're manually coding this up?
Yeah, okay. So the question is, when you do stochastic gradient descent, you need to sample a subset. So is there a magic number for the size of the subset? The answer is no. yes, the people often use the numbers, small numbers like 32 and 64 and 128. These are kind of arbitrary. On your data set, typically you need to do some trial and error. And the kind of trial and error you do is you need to monitor the loss curve. If you see that the loss curve is decreasing in a good shape, not like this kind of shape, that's suggesting things may be going right way, but it's not a definite thing. Yeah. Yeah. Okay.
Hi, thank you for the brief introduction. I'm no expert in neural networks, but my question is regarding UNIT,
Yeah.
which is also a convolution neural network. So when you train models, if you have data set where you, for example, an image where you have two types of pixels, one from biological sample, one from the background that is generated. So sometimes you can generate background, basically saying that, yeah, I've segmented the image, generated the background. So those pixels have a inherently different saturation, hue, and many other properties. You skipped that part, which
Yeah.
I was quite interested in, but yeah. So how do you tell the software that, so it does seem like very simple when we are trying to train these models many a times, since we are just clicking on pixels and telling, okay, this is my area of interest, this is not my area of interest.
Yeah.
But how can you specify specific inherent properties that you're looking for in that image?
So the question is about how you can specify the property that you are interested in the data, or is it
Within the data.
within data? Yeah, so the question is, for example, if you want to do dealing with images, you want to identify regions of interest, how do we actually specify that? I think unfortunately you probably have to do it manually, but maybe with some AI agents, because nowadays for doing segmentation, there are some what we call the foundation models. They can already do some pretty good job for generating reasonable initial segmentations for you. And with those tools, then you can try to now do a bit manual correction. Yeah. So for the data part, then yes, you still need to do the hard work. Yeah.
Thank you.
I think there'll be some more talks that will focus a little more on that today and also on those who. Yeah. I think maybe we'll just do one more before. I think we have some online questions that we might.
Yeah. Let me just take the last one. According to the Nofri, it's more complex model better than a simple model, or. Okay, so that's a very complicated question. Yeah, so but what the no free lunch theorem says is basically, for all the machine learning algorithms, none of them is consistently better than all the others across all the problems. Right? So that's kind of not surprising. If you already have a kind of the best possible algorithm, then we can just forget about what I have said here. Just run the algorithm and solve your problem. Now. Where is the? Oops.
Just and we need to wrap it up.
Yeah. So now the what that means is indeed simple, whether it's a simple model or it's a complicated model, you can't guarantee they're consistently better. You need to choose the model's complexity according to your problem. So that's actually the art part of applying machine learning. You need to develop a sense of whether a model is reasonably expressive for capturing the relationship between your input and output. Yeah. Okay, that's the short answer. Yeah.
Thank you, Nan.